Hello and welcome to online lecture number 14 for Chemistry 112 during the spring semester of 2020. In this lesson, we're still in chapter 17, and we get into something very important called cell potentials. Cell potential, also known as electromotive force, EMF, cell potential is abbreviated with capital E, is the force that spontaneously pushes the electrons away from the anode and towards the cathode. As we'll see, this cell potential is an indication, a measure of how much energy these electrons have. And the idea, the reason why electrons go spontaneously from the anode to the cathode is because electrons have lower energy on the cathode compared to the anode. So look at this example where we saw this was a spontaneous reaction, copper 2 plus ions plus zinc to produce elemental copper and zinc 2 plus ions, where copper will be reduced by zinc and zinc will be oxidized. So essentially zinc is losing electrons to the copper 2 plus ions. We kind of visualize why this is spontaneous because the electrons on the zinc have higher energy than they do on the copper. So the electrons on the cathode have less energy than the anode. So just like a ball rolling down the hill is spontaneous, electrons rolling, so to speak, from higher energy to lower energy is also going to be spontaneous. In our activity series of elements, we use this in the last lesson to predict whether a particular given redox reaction should be spontaneous or non-spontaneous. And we'll see that we have zinc and we have copper. So notice that elements like zinc that are higher up in this table have higher electron energy than elements that are lower in this table, like copper. So the reason why, as we talked about in the previous lesson, why elements are able to reduce ions below them is because electrons always flow from higher energy to lower energy, whereas the reverse, copper plus zinc 2 plus, there's no reaction, or at least there's no spontaneous reaction. It's a non-spontaneous reaction because this would be akin to, this is the picture showing the electrons being transferred from the copper to the zinc. So this would be akin to a ball rolling up the hill, going from a state of lower energy to a state of higher energy. It can happen, but it's not going to happen without ongoing outside intervention. So therefore, the process is non-spontaneous. Just like a ball rolling up a hill can happen, but it can only happen with ongoing outside intervention. As we get into electricity and electrochemical terminology, voltage is probably the most important of the terms for our purposes. It's a measure of how much energy these electrons have. In order to be a spontaneous reaction, the voltage, this potential, must be positive. The units are volts, and to relate volts to SI units, a volt is 1 joule per coulomb. So joule is the SI unit for energy, and coulomb is the SI unit for charge. So this is essentially a measure of how much energy each charge, each electron, in other words, has. Current, which is a related term, is a measure of the rate of electron flow. We use amperes or amps or A for the unit, and 1 amp is a 1 coulomb per second. So notice it's a rate of electron flow, coulombs, charge, per time second. And then finally, power, which is of most interest if you're interested in building a battery and you want to make sure the battery is going to produce enough power to literally power our devices. It's a measure at which we are able to convert that electrical energy into useful energy. We use watts, and 1 watt is energy per time, joules per second. So we notice that power, P, is just the product of voltage times the current. So P equals V times I, or equivalently, let's call the West Virginia notation, watts equals volts times amps. So either using the symbols for the different terms or their units, we can relate power is equal to the voltage times the current. So we saw that for a spontaneous reaction is spontaneous because the electrons at the cathode have less energy than they would at the anode. So electrons flow from higher energy at the anode to lower energy at the cathode. This will still be true for this reaction, Fe2 plus zinc. So notice that in this spontaneous reaction, zinc is donating 2 electrons to the Fe2 plus to reduce Fe2 plus to elemental iron. And we can predict that that should happen because we have zinc and we have iron And zinc, like with copper, zinc is above iron on this activity series. So as we would predict, zinc should be able to reduce Fe2 plus because elemental zinc is above Fe2 plus on our activity series. So just like with copper, it is above, so it is a spontaneous reaction. But notice it's not as high above compared to the copper example. So yes, zinc is above iron, but that distance, that difference in their even relative ordering is much smaller than compared to zinc versus copper. So yes, the process is still spontaneous. Electrons will still flow. The ball, so to speak, rolls down the hill. But just like rolling the ball down a steep hill, like with the zinc copper example, versus more of a shallow hill, yes, the ball still rolls down the hill, but the electrons still flow from the anode to the cathode spontaneously. But because this difference in the electron energy is not as great as what we saw with the zinc copper example, yes, the electrons flow, but they flow with less energy relative to the copper zinc cell. So as a result, comparing these two, they're both spontaneous reactions, but would expect that the spontaneous generation of electrons, spontaneous movement of electrons from the anode to the cathode for the zinc copper cell versus the zinc iron cell. In the zinc copper cell, those electrons will have more energy associated with them, so therefore a higher cell potential compared to the zinc iron cell. And so we'll talk a bit in a moment or two about how to calculate these numbers, but what we will find, both by calculations as well as we could demonstrate this in lab, that we get positive potentials in both cases, but the zinc copper cell is much more positive than that of the zinc iron cell. In other words, the energy of the electrons flowing from the zinc anode to the copper cathode is much higher, over 3 times higher under standard conditions, compared to the same electrons flowing from the zinc anode to an iron cathode. So your choice of anode and cathode, as we'll see, makes a huge difference in determining, at the very least, the potential of our cell, how much energy these electrons have. And as we saw, potential, the volts associated, does play a role in determining how much power our battery would be able to provide. So like we've seen before in other types of properties of reactions or even properties of substances themselves, the cell potential is also a property of a reaction, of a process, that depends upon a variety of factors. As we've already seen, it depends upon the identity of the electrodes. For example, whether we're dealing with a zinc and copper electrode or a zinc and iron electrode, as well as the concentration of all products and reactants. In fact, you can actually create a battery, a galvanic cell, using the same type of electrode as anode and cathode, and the only difference is in the concentration of their ions, as well as the temperature of the cell. So as we've seen before, just to make sure that everyone is able to compare apples and apples, typically when we find values in tables, for example, table in our book, what's listed will be the standard cell potentials. And it's the potential of that cell under standard conditions. And those standard conditions are the same standard conditions we've seen in other contexts, where the concentrations of all solutes is exactly 1 molar, the partial pressures of all gases is exactly 1 atmosphere, and any solids and liquids that are part of this process are in their pure form, or pure substances. If we want to be able to determine the relative reduction potentials or relative oxidation potentials, we want to be able to predict what the actual cell potential will be given what the identity of the cathode and anodes are. We can do that with this equation. Very simple equation that says that the standard cell potential is just equal to the difference in the potential at the cathode minus the potential at the anode. And in this equation, these potentials are the potentials for the reduction half reactions. Even though oxidation occurs at the anode, as we know, we still use the reduction half reaction potential number for this equation. So if we want to determine what these relative reduction potentials are, what the actual reduction potentials are, we want to determine, in other words, for example, this number. What we actually measure, though, is E cell. And that's the only thing we can measure. So if I have this sort of setup, or for example, I want to determine what the reduction potential is of copper 2 plus being reduced to elemental copper, then I could set up this cell, and so I'm interested in this number, what I'm actually measuring here, this positive 0.337 volts, that's the cell potential. And that cell potential is due to both what the reduction potential is at the cathode as well as what the reduction potential is at the anode. So to resolve this issue where we're interested in this number, but all we can measure is this number, and this number depends upon these two numbers, what we do is that we establish the anode as a standard anode. And typically most tables give us values that are based upon the so-called standard hydrogen electrode, or SHE, where we have hydrogen gas at 1 molar hydrogen ions and 1 atmosphere hydrogen gas. So everything's under standard conditions. And we define the reduction potential of the anode as exactly 0.00 volts. So this is what we're interested, how we're able to calculate the cell potential, predict the cell potential. We're defining, though, the anode potential as 0.00 volts. And because we're defining the anode potential as exactly 0.00 volts, this number is 0.00 volts. As a result, then, very important conclusion, is that the cell potential that we measure is then equal to the reduction potential of whatever is serving as our cathode. But keep in mind, though, that these numbers are all relative to the definition of defining the anode potential as 0.00 volts. And as said in our table in our book, and as most commonly found, is that these values then are versus or relative to that standard hydrogen electrode. So consequently, then the reduction potential at the cathode is then equal to our cell potential. So now the cell potential, what we can measure, is equal to our reduction potential of the cathode. So we can just continue doing these experiments where we keep the standard hydrogen electrode in each case, and we just trade out the cathode for different elements: copper immersed in copper 2 plus ions and 1 molar copper 2 plus ions, zinc immersed in 1 molar zinc 2 plus ions, iron immersed in 1 molar Fe 2 plus ions, etc., to find what these relative reduction potentials are of these elements. And so as a result, then, this experiment would show us that the reduction potential of this copper 2 plus half reaction is equal to our cell potential, which is equal to, in this case, about 0.337 volts. So we can go through that same process for a variety of different elements. And this is just a sampling of the numbers that we know. This is from Appendix L of our textbook. It shows that, of course, by definition, the standard hydrogen electrode under standard conditions will have a reduction potential of 0.00 volts. Copper, as we saw, is slightly positive. Oxygen, iodine are more positive, and these other elements are more negative. You'll notice, though, that this ordering of elements is the opposite of the ordering elements we saw with the activity series. And that's intentional because the activity series, if you recall, was an ordering from the easiest to be oxidized to the hardest to be oxidized. It was a ranking of how easy it is for those elements to lose electrons. Whereas this is a listing of reduction half reactions. So this is showing from most positive to most negative the relative ability of these substances to be reduced, to gain electrons as part of that process. So that's why the ordering is different. That's why we saw zinc was above copper in the activity series, but here it's below copper. So qualitatively, in other words, qualitatively, we can use the activity series just to predict whether or not a particular process will be spontaneous or non-spontaneous. But if we want to calculate cell potentials, we need numbers. We need these reduction potentials of these half reactions. And so that's where we use a table such as this one. So to illustrate, we have our spontaneous reaction of copper 2 plus zinc produces elemental copper and zinc 2 plus. And we want to calculate the standard cell potential given the reduction half reaction potentials of the two elements. So we have copper and we have zinc. So the only thing we need to really worry about is, based upon the given overall reaction, what is occurring at the cathode and what is occurring at the anode. Because when we're according to our equation, E cell is equal to, what you're saying, is equal to E cathode minus E anode. So at the cathode is where reduction always occurs, and at the anode is where oxidation always occurs. So if I recognize that copper is being reduced, That means copper must be serving as the cathode in this example. Zinc is being oxidized, which must mean that zinc is being serving as the anode. So to calculate this cell potential, so when we plug those numbers in, the cell potential is equal to the reduction potential of the cathode, which is copper, which was 0.34 volts relative to the standard hydrogen electrode, minus the reduction potential of what's current at the anode, which is zinc, which was a negative 0.76 volts. So that difference, positive 0.34 minus a minus 0.76, gives us a value of positive 1.10 volts. So notice it's positive cell potential, which means it's spontaneous, as we've been talking about all along, and it's a positive 1.1 volts. So that gives us an idea as how much energy these electrons have for this cell under standard conditions. And as another example, we have a balanced redox reaction. Aluminum plus Fe2 plus produces aluminum 3 plus iron. And notice that aluminum is being oxidized from an oxidation number of 0 to positive 3. Iron is being reduced from positive 2 to 0. So because aluminum is being oxidized, that means that aluminum is our anode. Iron is being reduced, which means iron is our cathode. So to calculate the cell potential, we'll take the reduction potential at the cathode, the iron number, and from that, we subtract the reduction potential of what's occurring at the anode, which is aluminum, the negative 1.66. So when we plug in our numbers, we have negative 0.45 volts minus a negative 1.66 volts to give us a predicted standard cell potential of negative 0.45 minus a negative 1.66, a standard cell potential of positive 1.21 volts. So like the copper zinc example we looked in the previous slide, it's positive, so it's a spontaneous reaction. This number is more positive than the copper zinc, so we'd expect that in this particular cell, the electrons would have slightly more energy than they would in the copper zinc cell. And for our last example, look at this one where magnesium 2 plus reacting with iodine ions to produce elemental magnesium and elemental iodine. So remember the equation is E cell equals E cathode minus E anode. So all we have to do is recognize what is the cathode and what is the anode. The cathode is always where the reduction is occurring. The anode is always where the oxidation is occurring. So we can see then that magnesium is being reduced from positive 2 oxidation number to 0, which means that magnesium is our cathode. Iodide is being oxidized from iodide to iodine, which means that iodide is serving as our anode. So when we plug in the respective numbers into our equation, we have E cell under standard conditions is equal to negative 2.37 volts minus the standard reduction potential at the anode of iodide is 0.54 volts. So our standard cell potential for the cell would be negative 2.37 minus 0.54 for a value of negative 2.91 volts. Thus, in contrast to this example compared to the previous two examples, we get a negative cell potential under standard conditions, which means that under standard conditions, that particular reaction we saw in the previous slide is non-spontaneous. The reverse of that process would in fact be spontaneous. As yes, this number tells me what the cell potential should be under standard conditions, but how can I calculate, how can I predict what the cell potential would be, the energy of my electrons would be under my experimental conditions, which a lot of times, most of the time, are not these standard conditions? Is there an equation that will relate these standard cell potentials to non-standard cell potentials? And that's part of what we'll talk about in the next lesson.